Today, we're going to talk about the Pitot-Static System, a critical component that powers some of the most important flight instruments in an aircraft. These instruments are essential for any pilot, as they provide crucial flight data that determines how an airplane is flown. In any aircraft, we'll typically find 6 basic flight instruments, commonly referred to as the 6-pack. These are airspeed indicator, attitude indicator, altimeter, turn coordinator, heading indicator, and vertical speed indicator. Knowing what these instruments indicate is important, but understanding how they work is just as essential. 3 of these instruments, the airspeed indicator, altimeter, and vertical speed indicator, use air pressure to function. The other 3, the attitude indicator, heading indicator, and turn coordinator, work based on gyroscopic principles. In this video, we'll focus on the system that allows those pressure-based instruments to operate. The Pitot-Static System. The Pitot-Static System measures air pressure and feeds it to the relevant flight instruments. But it's not as simple as measuring just one type of pressure. There are actually 3 types of air pressure involved. 1. Static pressure. 2. Dynamic pressure. And 3. Total pressure. Let's define each one before diving into how the system works. Static pressure, also known as atmospheric pressure, is the pressure air exerts on objects in the atmosphere. It's evenly distributed around an object, whether the object is stationary or moving. Static pressure varies with altitude. At sea level, it's about 1,013 hectopascals under standard conditions. As altitude increases, the air column above you decreases, and so the pressure also decreases. This is why, for example, pressure at the top of a mountain is much lower than at its base. On average, static pressure drops by 1 hectopascal for every 30 feet of altitude gained, or drops by 1 inch of mercury for every 1,000 feet of altitude gained. This behavior isn't unique to air. It also occurs in fluids like water. In a swimming pool, for example, you'll feel more pressure the deeper you go. That change in pressure is similar to how static pressure decreases with altitude in the atmosphere. Next, we have dynamic pressure. This is the pressure air exerts on an object moving through it. It increases with speed and air density. So, if an aircraft is flying at 100 knots, the dynamic pressure is lower than at 140 knots. It always acts opposite to the direction of motion. Total pressure, also called Pitot pressure, is simply the sum of static pressure and dynamic pressure. Think of sticking your hand out of a moving car window. Your palm feels both the still air, static pressure, and the air hitting it, dynamic pressure. Together, that's total pressure, just like what an aircraft measures in flight. Now that we understand the pressures, let's look at the Pitot-Static System itself. It includes 2 main components, the Pitot Tube and the static port. These feed data to the airspeed indicator, altimeter, and vertical speed indicator. The Pitot Tube measures total pressure. Let's look at the instruments one by one. First, I'll start with the airspeed indicator. The airspeed indicator is the only instrument that uses both the Pitot Tube and the static port. As the aircraft moves, air exerts pressure against its motion. This is called dynamic pressure. The Pitot Tube facing the oncoming wind measures this dynamic pressure along with the static pressure. Together, this is called total pressure. To calculate airspeed accurately, we need to separate the dynamic pressure from the total pressure. Since static pressure changes with altitude and weather, the static port provides a constant reading of the current atmospheric pressure. This allows the system to subtract it and display the correct airspeed. The airspeed indicator uses inputs from both the Pitot Tube and the static port, separated by a diaphragm. Static pressure fills the airspeed indicator's case, while the Pitot Tube sends total pressure to the diaphragm. The difference between these pressures creates dynamic pressure, causing the diaphragm to move. This movement drives the airspeed indicator's needle, and it is showing airspeed to the pilot. Remember, the airspeed indicator measures airflow relative to the aircraft, so strong wind gusts or turbulence can affect its readings. The second one is altimeter. The atmospheric or static pressure varies with altitude and weather. The altimeter uses the input from the static port to determine the altitude. The altimeter is the only instrument in small aircraft that gives the pilot altitude information. The altimeter measures altitude by comparing static pressure in its sealed chamber to a fixed pressure inside a diaphragm, set at 1,013 hectopascals, or 299 millibars, 2 inches of mercury in the standard atmosphere conditions. As the aircraft climbs and static pressure decreases, the pressure difference moves the diaphragm, which turns the altimeter's needles. Since atmospheric pressure changes with weather, pilots must adjust the altimeter using the local barometric pressure shown in the Colesman window. If not adjusted, altitude readings may be inaccurate, risking collisions or terrain hazards. Temperature also affects the altimeter. Colder air makes your true altitude lower than indicated, so pilots should account for this, especially over mountains. I have detailed video about the altimeter. If you want to know more about it, you can watch the video. Now let's continue with last instrument, which is vertical speed indicator. The vertical speed indicator also relies solely on the static pressure input. As the name implies, the vertical speed indicator shows the rate of the aircraft's climb or descent. It shows the rate of climb or descent in feet per minute. When you're flying at a constant altitude, it should indicate 0 if it's been calibrated properly. In the vertical speed indicator's case, the static pressure enters the instrument through the static pressure line that you can see in the diagram. This line connects to the inside of the diaphragm. The static line also has a restricted hole that leaks pressure at a calibrated rate to the instrument casing. Both of the inputs come from the static port, but the inside of the diaphragm has an unrestricted opening, and the vertical speed indicator case has a metered opening. When the aircraft climbs or descends, the static pressure will change instantly in the unrestricted opening, but the case pressure will take longer to adjust because of the restricted opening. This creates differential pressure acting on the diaphragm, which then moves and rotates the connected needle too. The faster the rate of climb or descent, the greater the differential pressure, and the more the needle will swing. So where is the Pitot tube on the aircraft? The Pitot tube measures total pressure and is typically mounted on the wing or nose. It must be aligned with the aircraft's longitudinal axis and located in undisturbed airflow. Any interference, such as from the propeller or wing, can lead to inaccurate readings. To prevent ice blockage, Pitot tubes have heating elements. The heating system is activated from the cockpit, usually with a switch labeled Pitot Heat. They also include a drain hole to expel water, especially when flying in rain or when ice melts. Despite the precautions, the Pitot tube can still be affected by position errors. When the aircraft is flying at high angles of attack, airflow becomes misaligned with the tube. This misalignment can slightly distort total pressure readings. On the ground, the Pitot tube should be covered to prevent dirt, water, or insects from clogging it. The cover is usually marked with "Remove before flight" as a visual reminder to the pilot. The static port is a small hole, usually on the side of the fuselage, designed to measure static pressure only. It's positioned to avoid dynamic pressure, allowing for accurate atmospheric readings. However, skidding, sliding, or even deploying flaps or gear can disturb airflow and introduce slight errors. If the static port becomes blocked, for example by ice pilots, can switch to an alternate static source. This backup port is often located inside the cockpit, where it's shielded from external conditions. However, cabin air pressure is slightly different from exterior pressure. In multi-engine aircraft, there are often two independent Pitot-Static systems, one for the pilot and one for the co-pilot. This provides redundancy and allows for cross-checking between instruments to detect inconsistencies or malfunctions. Before we finish the topic, these instruments may have few errors in the air. What happened if they are blocked? The Pitot tube and static ports are exposed to ice, dirt, moisture, or insects. If they're blocked, your instruments can give false or no readings. In instrument meteorological conditions, you must rely on instruments, so knowing how to diagnose these issues is critical. Blocked Pitot tube with clear drain hole. If the Pitot tube is blocked but the drain hole stays open, air escapes and the airspeed indicator drops to 0 as pressures equalize. Blocked Pitot tube and drain hole. If both are blocked, trapped pressure prevents the airspeed indicator from measuring airspeed. At a steady altitude, it will display a constant, unchanging speed. During a climb, it shows increasing airspeed. During descent, it shows decreasing airspeed, regardless of actual speed. This can mislead you into reducing throttle, risking a stall. Blocked static port. A blocked static port traps pressure, affecting all three instruments. The vertical speed indicator shows 0, the altimeter freezes, and the airspeed indicator gives incorrect readings. The farther you fly from the blockage altitude, the greater the ASI error. showing higher speeds during descent and lower speeds during climbs. So now you know how the Pitot-Static System works and why it's such a critical part of aviation. It's more than just tubes and sensors. It's the system that helps pilots stay informed, safe, and in control. The more you know, the safer you'll feel on your next flight. If you found this video helpful, don't forget to like, share, subscribe, and leave a comment below. Thanks for watching.